Hello friends, it's raining cats and dog outside, so it's the best time to deal with the laws of nature, to deal with physics. So let's have a magnet. Let's start with a magnet. This is a magnet which we use in our daily life experiences. So let's say this one is North Pole and this one is South Pole. And let's bring a piece of iron filing near this magnet. So what will happen? Everyone knows this iron filing gets attracted towards this magnet. But how this iron filing gets attracted towards this magnet? What's the cause? Is there a gravitational force of attraction? Yes, there is a gravitational force of attraction, in fact, but gravitational force of attraction is due to the virtue of their masses, and these masses are very low, so this gravitational force of attraction will be negligible in comparison to something else. So is that an electrostatic force? No, this is not an electrostatic force, because this one is not a charge and this one is not a charge. So then why this iron filing gets attracted towards this magnet if gravitational force is very negligible in comparison to something else, and apart from that there is no electrostatic force because this one is not a charge and this one is not a charge. So what could be the reason behind that? Yeah, definitely, you are a clever guy, my dear friend, you are a clever guy, and you will tell that, okay, fine sir, the reason behind that is that this iron filing gets magnetized. That's why this gets attracted towards this magnet, because this iron filing gets magnetized. But my question is that, from where does this magnetic field come, or from where does this magnetic force come? What is the cause of this magnetic field? Or is this field a fake one? Or is this field a lie? Or I can say, is this field a mystery? Or is this mysterious? Or is this an illusion? Is magnetic field an illusion? Is magnetic field a lie? Is magnetic field a mystery? What's that? From where does this force come? Now let's take another scenario. Let's have a conductor. This is a typical conductor, and let's bring a small positive charge Q near this conductor. What will happen? Nothing will happen. In fact, I mean to say that this conductor is not going to apply force on this Q charge, and this Q charge is not going to apply force on this conductor. And in fact, if you are going to talk about their masses, the gravitational force of attraction is very less in comparison to something else. And apart from this one, this is electrically neutral. If you look at this conductor is electrically neutral. So if this one is electrically neutral, so this cannot apply force on this one, and this is not going to experience any force, and at the same time I must say this is not going to apply force on this one. So this conductor is electrically neutral. Now what will happen if electricity passes through this conductor? Or in other words, you will say that if electrons are moving through the conductor, if electricity passes through the conductor, what will happen? How electricity passes through the conductor? We are going to put this conductor in the electrical circuit, and we will close the circuit, so electricity passes through this conductor. The first case was that it was just a conductor, so the conductor was electrically neutral. It was not going to apply any force on the charge. And now the second case is that the current is passing through this conductor. Fine, folks. The current is passing through this conductor. But still, this conductor will not apply any force on this charge. Why this conductor will not apply any force on this charge? Because still this conductor is electrically neutral. If a current passes through this conductor, the conductor is electrically neutral. Still it's electrically neutral. I will be explaining the cause in the later part of the same video. But this conductor is not going to do anything even if the current passes. Now what we are going to do, I will take off this charge and I will shoot the same positive charge in the right direction. Same positive charge in the right direction with a velocity v here. It's a huge velocity. So right now the charge is moving and the charge will experience a force. It will get deflected. It will get deflected. So the first case was the charge was not moving. It was not going to experience any force. But in this case, if charge is moving, if we shoot a positive charge with a velocity v in the right direction, the charge is moving. Now it's going to experience a force here. So if I will be asking you the reason, first of all, you tell me that what's that? This one. This is a magnet, in fact. This one is a magnet. If electricity passes through a conductor, it's a magnet. It behaves as a magnet. So this one is a magnet. This one is an electromagnet. So what I'm doing here, I'm just shooting a positive charge here with a velocity of v in the right direction. So what will happen? This positive charge will experience a force. But when the positive charge was at rest, it was not going to experience any force. Fine. So if I am going to ask you the reason, what will you tell? You will tell, okay sir, fine, what's the big deal here? The reason behind that is that one. This one is a magnet, in fact. This one is an electromagnet. And this one is a moving charge. So a moving charge behaves as a magnet. So that's why the magnetic field is created. The magnetic force is getting experienced. Because this is a moving charge and this moving charge behaves as a magnet. But my question is that it's still the same one. From where does this magnetic field come? From where does this magnetic force come? Or is this an illusion? Is this a mystery or something else? So this right now we are going to discuss. So before dealing with the regions, let me introduce you to a special theory of relativity that was proposed by great Albert Einstein in 1905. And believe me folks, it was no less than a revolution in the world of physics. So we'll be dealing with one of the consequences of spatial theory of relativity. That's the space contraction, or in other words you can say it's a length contraction. So what length contraction says, if an object is in motion, if it is in motion, it appears to be shortened in the direction of the motion itself. When an object moves with a huge velocity, in fact, when an object moves with a velocity, or when an object is in motion, its length gets shortened, or it gets contracted in the direction of the motion itself. Let's take an example here. If this is a typical car, and this one is Mr. Anderson, and Mr. Anderson is my friend. So this one is Mr. Anderson, and he is on the earth, and this is a car, and this car moves with a velocity v, and this velocity v is a huge one. This velocity v is huge velocity. So this car appears to get shortened. This car will appear short. The length of this car will get contracted. It will be appeared as if it gets contracted. Is that clear? So this car will appear short to this Mr. Anderson. So this is the length contraction. So we are going to use this idea. Oh, sorry, I beg my pardon. I must not tell this an idea. It's indeed a revolution. This spatial theory of relativity is a revolution. So in fact, I will use this one. I will use spatial theory of relativity to explain the questions asked by me. Fine. So before that, I must advise you to pause the video and just note down these steps. Before dealing with the regions, let me give one add-on the length contraction on the spatial theory of relativity. So in our daily life experiences, we do not counter with this length contraction. We do not see this length contraction because our velocity, our speeds, our velocities are very less in comparison to the velocity of light. So whenever some object goes with closer to the velocity of light, to the speed of light, then it is getting experienced. If it moves with a huge velocity, then it is getting experienced. But in our daily life experiences, we don't counter with these huge speeds, and that might be the reason behind that we do not experience the length contraction. And apart from this one, let me clarify one thing, that when the current passes through the conductor is still electrically neutral. So fine. Let's have this a conductor. This one is a conductor, and I say that current is flowing. The current is flowing. Electrons are flowing. Fine. The current is passing through this conductor, and if we look the positives, these are the positives, and these positives are stuck. These are not moving. These positives are stuck, in fact. So still at every portion, at every part of the wire, the positives and negatives are equal, or you can say each part of the wire is neutral. So the net effect is, this one is electrically neutral, and in fact this one is neutral. This behaves as a neutral. Fine, is that clear? Each part, if we look at each part of the wire, still when the current is flowing, that is a neutral one, because the number of positives is equal to the number of negatives. And at the same time, I must add on that when we apply potential difference across the ends, the electrons are drifted and at any instant the number of electrons are equal to the number of protons. That's why this one is electrically neutral. Fine points. Now let me deal with the regions behind the magnetic field, why it is getting produced. So let me take a magnet. This is a typical magnet. This one is a magnet. The electrons are moving. The electrons are moving with a velocity v. Fine. And in fact, this is a magnet. Why this is a magnet? In fact, this is in fact an electromagnet, because electricity is passing through this conductor. That's why this one is an electromagnet. So that's why I told you that this one is a magnet. Now what I do, I shoot a positive charge with the same velocity v in the right direction, and let's ride on this positive charge. What I am doing, I'm taking this electromagnet, I'm taking a conductor, and the current is passing through this conductor. In fact, the electrons are moving with velocity v, and what I'm doing, I shoot a positive charge with the same velocity, and this positive charge is moving with the same velocity in the right direction. So let's ride on this positive charge. That means let's deal from the reference of the positive charge. Taking this positive charge as my frame of reference, let's deal everything from the reference from the positive charge. So when I am at the positive charge, or with respect to the positive charge, the electrons are not moving. Is that clear? Is that clear? This one is a very useful notion behind dealing with those regions. Fine. This one is a very useful notion. So if you are on this chart, or if you view electrons with respect to this charge, these electrons are stationary. These electrons are not moving. But what about these positives? What about this positives? What about this positives? These positives are moving. These positives are moving in this direction with the same velocity v. With the same speed v in this direction, in the opposite direction. Is that clear? When I view the positives from this, from this charge, what it seems to me that these positives are moving in this direction with the velocity v. Now recall length contraction. What's that length contraction? So these positives will appear shorter. These positives will get shortened. The length will, the length will get shortened. It will get contracted along the direction of the motion. So it will appear like this one. It will appear like this one. It will appear like this one. Like this one, like this one. Now, let's deal with a particular section of the wire, or a particular layer of the wire, or a particular pad of the wire. So each pad of the wire is a positive one. Is that clear? Each part of the wire gives you the positive effects. Each part of the wire is positively charged. You can say that the linear charge density of the positives become less. So each section here, each part of the wire is positive and the net effect is positive. So this one is positive. When we are dealing with respect to this charge Q, this conductor is positive and this charge is positive. This is going to repel this positive, and this positive will get deflected away. Is that clear? This positive will get deflected away. So that's the reason that if this charge is moving, this will get deflected away. Now let me deal the thing with the Earth's perspective. So with the Earth's perspective, in fact this will get deflected. Is that clear? When I'm going to view from the Earth, the same visibility will appear. I will see that this charge is getting deflected. It's moving, gets deflected. Fine. Is that clear? So now let's deal with the frame of reference of this charge. I will say that it's nothing new. It's an electric force. It's an electric force because I am positive and this one is positive. So positive is going to apply force. Both are charged. That's why this is nothing. This is no new thing. Is that clear? But for me, it appears something new. For me, it appears something new, and I will tell that it's nothing but the magnetic field or magnetic force. Is that clear? It's nothing but the magnetic field. So what's that magnetic field? Magnetic field is nothing but the electric field when viewed from another frame of reference. This one is magnetic field. Okay, fine. This is a magnetic field. When I view this situation, I'm telling that okay, this must be a magnetic field. But with respect to this charge, it's nothing new. It's just the force. It's just the force. This one is a charge and this one is a charge, because when we are dealing with respect to this charge, this whole conductor appears to be positive. So this one is positively charged and this one is positively charged. That's why this gets deflected. Is that clear? So it's nothing new. This one is electric field. This one is electric field. So I will say that magnetic field is nothing but the electric field viewed from another frame of reference. Is that clear? Hope the things have been clarified. You have enjoyed the video. So do subscribe and share the same. Thank you.